Now we're going to turn our attention to the problem of finding the antiderivatives of more types of functions. Not always more complicated functions, and yes, some of them are complicated, and hence the techniques will be more advanced. But it's just the idea that there are some functions out there, some simple functions for which we don't have a basic rule, and a U substitution won't work. And right now, those are the only two ways that we have for finding antiderivatives. We reverse a simple result from Calc 1, or we try to use a U sub and maybe some clever tricks in algebra to get something to work, but those clever tricks don't always work, right? So the first of the integration techniques that we're going to look at is something called integration by parts, right? And probably a good place to start is by saying this. The chain rule from Calc 1 led us to the idea of the substitution technique, right? That's basically it. In fact, let me kind of do this. So like one will undo the other. So based on what the chain rule told us in Calc 1, we derived this process for a substitution. But in order for the chain rule to work, again, that pattern has to be there. Like we have to see that like inner function, and then we have to see like a constant multiple of the derivative of that inner function multiplying on the outside. So, even just to say it, there's a lot there, right? Well, it turns out of course, we have other rules from Calc 1, right? And the rule that we're going to work with to come up with this technique called integration by parts is the product rule, right? So let me just kind of remind you of the product rule. So the product rule says if I'm taking the derivative of the product of two functions, and they're usually written like this. Well, it says, and I'm going to do it the way I typically say it. It's the derivative of the first function times the second function plus the first function times the derivative of the second, right? Now, so F and G are used a lot when you state the general product rule. But a lot of times you might see the letters U and V. So let's do that. Just for fun, let's replace all the F's with U and then all the G's with V's, right? So if we do this, I mean, why not? Why not just, mix it up a bit? So do this, right? In fact, some people like to state the product rule in terms of U and V instead of F and G. So this would be U prime of X times V of X plus U of X times V prime of X. Now, suppose it is assumed that U and V are functions of X. So what if we don't have to write the of X part? So what if we just get rid of that, right? What if we just get rid of these? Where are we? All of these. Just get rid of them. And then since I used the D notation on this side, let's be consistent and use the D notation on the other side, right? So what if I did this? So now let me switch back to my white chalk here. So I have d dx, and then I have just u times v, just like that. And then instead of writing u prime, I'm going to use the d, or the Leibniz notation, for these derivatives as well. So this will be du dx times v, and then plus u times dv dx. And you're probably sitting there waiting, okay, where's the punchline? All I'm doing is just rewriting things. Okay, well, I'm going to keep rewriting things. And I know you're going to stay tuned to see where is this going, right? Where's the cliffhanger? So now what I'm going to do is write these derivatives in differential form. Now remember what differential form is. That's when you literally multiply both sides by your dx. But if I do that, because every term here has a dx in the, again, you call it a denominator, but technically these are not fractions per se, but we manipulate them like they are fractions. But if I multiply both sides by dx, and formally what that means is I'm putting this in differential form, then the dx's will completely go away. So I can write the product rule, right, in this differential form using the letters u and v, and it looks like this. So the differential form of the product rule says if I take the derivative of uv, I'm going to get du times v plus u times dv. And again, some books, some websites, lots of resources state the product rule like this. In fact, they go even a step further. What they might do is, since this is a product right here, it's this differential times this function. Since it's a times, I can write it as v du and then plus u dv, right? So this is another version of the product rule, right? Now, why is this important? Because now, what if I integrated both sides, right? So now that I have this in this much simpler form than where I started. Look at where we started with all the x's and the parentheses and the brackets and dx all over the place, just a mess. This is just such a cleaner form of the statement, right? Now if I integrate both sides, so integrating both sides, what do we get? Well, let's do it. Let's do it. So it's the integral of that derivative of the product uv, and then that's equal to the integral of v times du plus the integral of u times dv. But what we know that when we take the an antiderivative of a derivative, it cancels out. You get back the original. So on the left hand side, I'm just going to have the product uv, and then on this side I have these two separate antiderivatives that I can't really simplify because this is a function, but then it's multiplied by a du, and then this is another function that happens to be multiplied by a dv. And there's no nice way to combine these two, right? Because the differentials are different, right? So there's no nice way to combine them. So I kind of have to leave them separate. But if I look at this equation, let's say I didn't want the two integrals to be on the same side. In other words, what if we isolated this integral, right? And the way I would do that is by subtracting this integral from both sides. Again, what would it look like? So let's see. So this implies, and let me write it this way, this by itself, so the integral of u dv is equal to this uv minus this other integral. So basically what I've done is move that integral to the other side of the equation. Thus, it picks up a negative sign in front of it, and I have this equation now. So it's the integral of u dv is equal to uv minus the integral of v du. And this is the famous, or sometimes infamous, integration by parts formula. And it just looks like an alphabet soup, right? So integration by parts. Now, here is the idea or the philosophy behind this technique. You or we will be given integrals on, and then we're going to say, okay, we're going to have an integral that we're going to match up with this. and it's an integral that we don't know or we don't have a nice result for just yet. Like I don't know how to integrate it. But if I can choose my u and dv wisely, and there is a very wise way of choosing, which of course I will tell you, right? If we choose our u and dv wisely, if we could then figure out these two parts over here, if we could figure out this product and then figure out this other differential and set up this second integral, the hope is that we would have made a good choice so that the integral on the right hand side of the equation is simpler to work with than the integral on the left hand side, right? So let's actually write that down. I mean, it's not a whole bunch of steps, right? It's very, very conceptual, this idea. It's not like always do this. No, we're gonna take this idea of being given one integral that we currently don't know how to evaluate it and see if we can break it into these two parts. One part is just a product. The other part is another integral, and the hope is that this integral on the right hand side is easier, or at least we know how to do this one, whereas this one we're just kind of, okay, I'm going to take a shot at this. All right. So the idea is to choose u and dv, right? And we'll give you a basis on which that choice can be made, right? So choose u and dv, and then find, look at what we need. We need v, because we don't have that, and du, right? So we're going to match up u and dv with the integral that we're given, and then we are going to have to figure out du and v and set up the expression on the right hand side with the hopes, and I say hope because yes, it is a hopeful process, right? But there will be some specifics to it. But find u and dv such that, right? Again, I'll put in parentheses, hopefully, this integral is, and I'll put in quotes, easier than the starting integral, u and dv, right? Because if that's the case, if in fact this one is easier, then this process is worth doing, right? If we end up just complicating it, then no, then yeah, our hope it has been dashed, right? So let's see how it works. And then I'll give you like a method as to, okay, in general, how do we make this choice? How do we make this educated guess, right? And which not really a guess, but in some sense, like I said, it's hopeful. So let's look at an example of a type of function that we currently, like based on just our simple antiderivative rules or a substitution, we wouldn't be able to do it. And a simple one is something like x times e to the x, right? Right, there is no, if you look at our basic, and when I say basic, if you look at our basic antiderivative rules, there is no rule for what to do when you have x times e to the x. And you look at it, there is no composite here, right? I mean, you can argue, you know, I mean, the e to the x is as almost as basic as it comes, and then it's being multiplied by another function, right? So let's see what we can do, and maybe come up with a way of making a choice. Look at it this way. If the x wasn't there at all, this would be a very, very easy integral, right? So the question is, could we make a choice in such a way? Because if you notice what happens, after we choose the u, we have to find du. That means I have to differentiate whatever I choose as my u, I have to find du, which is similar to what we do in a u sub, right? And we know, so if I were to choose my u to be x, right? I know that when I differentiate it, I will just get 1 dx. So the x would go away. So like on This side, where it says du, it would just be the same as dx, right? So that seems like it's a step in the right direction. So I've made a choice for u, and I'm choosing to use x as my u, because knowing that when I differentiate the x, it becomes simpler, so simple that it disappears. Poof, it's gone. Right? Well, if I choose u to be this, then it means everything else here would have to be dv. So I'd have to now my hands are forced, I would have to have that dv is e to the x dx. And then the question is, well, if this is dv, then what is v? Well, these are differentials. If I want to work backwards, I'd have to integrate it. So I would have to say that v is e to the x, right? Now, do I put my plus c here, or am I just looking for one of these? Like, do I want my constant of integration at this part of the process? No. Why don't we want the plus c right here? Because we're still going to have another integral to do. So basically we're choosing a simple u, hopefully, and a simple dv, which leads to an equally simple v that I can use now on the right hand side of this formula, right? Okay, so that's kind of the idea behind the choice. After this example, we'll make it a little bit more systematic, and it gives you a nice way to make this choice. So now let's apply in fact, let me leave the formula there as I write it down. So what this is saying, this technique is saying, if I take the integral of e to the x dx, I can break this integral into two parts. The first part is the product of u times v, but based on my choice, it's going to be x times e to the x, right? So I just did that part. Minus, and then I have to now have this other integral, and that integral is of v times du. Well, here is v. It's e to the x. Here is du. It's dx. And then I ask myself, was it worth the effort? Do I now know this integral as opposed to the one that I didn't know to start with? And I hope the answer is yes, because this is, again, is as one of our simple integrals. It's as simple as it gets. So then our final answer is going to be x e to the x minus, and then when I take the antiderivative of e to the x, I'll get my e to the x plus c. So this is where I put my constant, and now I claim that this is the antiderivative of my original function. How do I verify my claim? By checking. So let's take the derivative of what we think is the answer and see if we get back the original. All right? So here we go, fingers crossed. Right? Toes crossed, everything crossed. So d dx, so this is our check. Right? So if I now take the derivative, and you notice what's going to happen anytime you check a process like this, to work backwards, you will always have to differentiate a product. So you're going to have to use the product rule, right? So let's do this. So using the product rule, I'll have 1 times e to the x plus and then the first times the derivative of the second, so x times e to the x, then minus the derivative of e to the x, which is another e to the x, and then the derivative of the constant is 0. And look right here, this e to the x cancels out with this e to the x, and I am left with x e to the x, which is what I want. Right? So in fact, this is the antiderivative of x e to the x, right? And that, in a nutshell, is the integration by parts process. In some ways, I also like to describe this as a double substitution. Because notice there are two things we defined. Unlike the u sub where we just write down a u, we also have to write down this other equation, this dv. So I often refer to this as a double sub, right? And I should probably trademark that, but I won't, right? So it's like a double substitution. One just for, like a part of the function, like one of the factors in the function, and then the other substitution is for the remaining part times the differential, right? Okay, so as promised, I mentioned that there is a way that we can make this choice a lot clearer. In fact, so clear that I can say this with certainty. If we follow what I'm about to show you, is that we will be able to do 100% of our integration by parts problems. That's a bold claim, right? And I don't make bold claims easily, but yes, if you follow this, what I'm about to describe, at least this part of the process, right, is all good. Well, in fact, let me rephrase that. This part of the process, right, in terms of choosing u and dv, because once you make that choice, right away you're going to have to do a derivative here and an antiderivative there. Now, I can't guarantee that you'll always do those correctly, right? I'm hopeful, right? I think that's what's going to happen. But at the very least, I can give you a recipe for making the right choice for what u should be and what dv should be, all right? And what is this wonderful recipe? Well, it's an acronym that consists of 5 letters, right? LIATE. And actually, let me preface this. In like Southeast Asian countries, yeah, we're going to Southeast Asia now. They actually, many of the countries, they teach ILATE as opposed to LIATE, right? But anyway, so this letter, it's a letter that represents types of functions that you have studied up to this point. So going all the way back to the very first day that you heard about this idea of a function, right up to now, every function that you've used, right, including all those in those crazy piecewise functions, they fall into one of these categories, right? So basically, LIATE is going to be a description for every type of function that you'll come across, or that you have come across up to this point. It doesn't capture all the functions there are. There's so many special functions that go beyond the things that you learn in algebra and trig. But for what we need, this is the entirety, right? Okay, so what are these letters for? Well, the L is for logarithmic, right? So we know about logarithmic functions. The I is for inverse trigonometric. So your inverse trig functions. Notice we have never, up to this point, integrated a log function. Like what is the integral of the natural log of x? Well, we've never done that. Or what is the integral of arcsine or arctangent? We've never done that, right? That's not to say we've not used these functions, but up to this point we don't know how to anti-differentiate those functions. And my oh my, how quickly that will change. The A stands for algebraic. And that's a wide category of functions. And in the algebraic category, you have things like polynomials. Right? So you have polynomials, you have things like roots, so you have polynomials, you have roots, things like that, right? And then the T stands for trigonometric. Right, so the T stands for trigonometric, and then all that's missing now at the end, saving the best for last, is the exponent, and then you have exponential functions, right? Now, again, every type of function that you can write down that we've talked about, like whenever you see those questions, let f of x be equal to something, it's one or more of these types of functions combined together, right? Every one of them, right? So, how does Lie8 help us with this new process? Well, because Lie8 essentially is a way of categorizing all the types of functions that we need to know how to integrate in theory, right? This is how we make a choice. We're going to have to look at the function, the integrand that's given, and we're going to have to identify what types of functions are present in the integrand. So we're going to have to categorize them as a L times a or a T times a E, or a I times a. You know, so we're going to have to identify the types that are in there. And then, so if one of our functions in the VDU, so if a function is of, I should say, I left out the word is. So if a function is of one of these types, right? Or actually, no. Let me rephrase that. Let me state it this way. We define u as the function, right? As the function type whose letter comes first in Lie8, reading from left to right. So we define u as the function whose letter comes first in Lie8, right? Reading from left to right. Right, so reading from left to right. Again, what does that mean? So we're going to look at the functions that are present in our integral, and we are going to say, okay, I see a L type and a T type. And if that's the case, whichever function is the L type, that's the one that I would choose as u. And then by default, everything else would be defined as dv. So it's based on which letter comes first in Lie8, right? So it's basically a hierarchy, right? And then dv is defined as what is left over. Basically, the differential is defined as the differential, right? Because that's what we're going to have to integrate. So yeah, it would have to be the differential, right? All right, so let's take a look at Lie8 in play and see if we can actually apply it and make a good choice, right? So let's say, so here's another example. And well, in fact, we're going to do several examples now, actually a couple. So let's do the integral of, so let's say I have x squared times the natural log of x. Never been done so far, right? So we're trailblazing right now. Well, if we look at Lie8, well, I see a logarithmic function and I see a polynomial, which is an A type, right? So what I see in my problem is A type, right? Because that's a polynomial, and a polynomial falls in the algebraic category. And then I definitely see the L type. So these are the two types of functions, and they're being multiplied. That's going to be a big part of this type of problem. And because the functions are being multiplied, unfortunately, we cannot integrate them separately, right? We just can't. We couldn't do it for differentiation, so it's reasonable to think that we can't do it for integration. But because Ly8 starts with the letter L, right? The log function is going to take precedence over all other types of functions. So because the L comes first in Ly8, we're going to choose the U to be the natural log. So U will be the ln of x. And then once I've made my choice, everything else is going to be dv. The x squared is left over, the dx is left over, right? So it's like I've taken this part out of the product. I'm going to call that u, and then everything else, that's going to be dv, right? And then once I make this choice, similar to the u sub, we kind of kick into the mechanics of it. So this is the conceptual choice that we have to make at the start of the problem. Once you've chosen your u, we still differentiate it. So du, in this case, when I differentiate a natural log, it's 1 over x, and then I'll write it in differential form, right? So all these derivatives and everything are now written in differential form. And then for the dv, we want to figure out what v is, right? So I want a function that when I differentiate it will give me x squared. Well, that will be 1/3 x cubed. So now we have these 4 pieces that we can use to set up our integration by parts formula, right? So this is what it looks like. And I always start by saying, okay, here is our original problem. With this choice, and then subsequent du and v, I can write this based on what the integration by parts formula says. It says this product, the integral of this product can be expressed as u times v, so here's my u, times my v, minus the integral of v, which is 1/3 x cubed, times my du, which is 1 over x dx. Right? And then the question is this one easier to work with? And I think you can agree that it is. From the very nature of what we've done, I think it's clear that this integral on this side is easier. What made this one harder was the fact that there was now this ln, right? There was our natural log, and there was no u sub that we could choose here that would work. Because again, I don't have a composite. All I have is the product of these two things, right? But now with this choice, and with Ly8 guiding us, the second integral, right, doesn't have an ln anymore. All we have are essentially 2 power functions, and these 2 functions can be simplified, right? So before I integrate it, notice it's still a product, right? I started out with a product, I still have a product here, but the big difference is that this product can be simplified. Because if I have x cubed times 1 over x cubed, which is x cubed over 1, times 1 over x, is x cubed over x, which is x squared. So I'm able to break our original integral into these 2 parts or pieces, so that my second integral, I don't want to say is trivial, but it's a lot easier than what we started with. Now, the way I normally write this, just to make sure that we're not tempted to do any kind of invalid multiplication here, I tend to put first the constant, then the polynomial, then the logarithmic function. And the same thing would be like if it was a trigonometric function or an exponential function. I tend to put things in that particular order. This is how problems tend to be set up, right? There's nothing wrong if you leave it like this. It's just that I've seen, mistakes where you do some kind of product forgetting that you can't multiply through the ln, right? So it's less likely to happen if you put the polynomial in front. And then here, there's a 1/3 that we can factor out, right? And then we have an integral there. And then, like I said, x cubed times 1 over x, that simplifies to x squared. So undoubtedly, right? It's like magically the ln is gone, right? But not gone, it's just in a slightly different form, a form that's a lot easier for us to work with, right? So now I have 1/3 x cubed times the natural log of x minus 1/3. Do our power rule, right? For antiderivatives, so we get another 1/3 times x cubed, and this is where we put our plus c, right? So the final answer for the problem, what is the antiderivative of x squared times the natural log of x with respect to x? It is 1/3 x cubed ln of x minus 1/9 x cubed plus c, right? And what will happen with integration by parts? The more, again, I hesitate whenever I say the word complicated, but maybe that's what I will say, right? So the more complicated the function is, the less obvious, right, the antiderivative is. Because then it's like, because when you think about finding the derivative of this function and simplifying, it's not it's not a trivial problem, because you have to use your product rule there, and there are terms that you'll have to simplify. There's algebra you'd have to do. So because of what would be involved in checking this work, your answer might not be what you think it is. But that's why we have to build confidence in the method, right? To trust the method. In the method we trust, right? All right, so one more example, just so that we can build this confidence. So let's take another type of function that we have not integrated up to this point. So here's a second example in this group. What if we had something like, arctangent? So what if we had the antiderivative of arctangent? We've used arctangent before, but not in a problem where we had to integrate it. We've used arctangent because it is the antiderivative of a certain function. Now we're asking ourselves, what is its antiderivative? What function is it that when I differentiate it will give me arctangent? All right? Well, let's see. So we have, let's put our little I8 there. And the I stands for inverse trig, right? And you might say, well, I don't see a product. Well, here, if you want me to make it super clear, yes, there is a product there. It's arctangent times 1 times dx. And 1 is a constant. In fact, if you think of it, it would be like a constant polynomial, right? So it's like we have an inverse trig function times an algebraic function, so the I takes precedence over the A, right? So this is my I type. This is my A type. And by the rules our guidance given by Lie8, our U is going to be arctangent, right? So let's write that down. So we're going to make, so U is going to be arctangent of X. And then by default, everything else is dV, right? So we'll have that dV is 1 dx, or just dx, right? So again, here's our double sub, right? I just like saying that it's a double sub. And then we're going to differentiate the u, so we'll have du, that's equal to 1 over 1 plus x squared dx, right? Which again, you see that this is the part I was mentioning, that, yeah, Lie8 tells us what to choose as u and dv, but then we still are going to have to know how to differentiate it, right? So even the derivative at this point, might be a little tricky. But we just have to work through it, utilize what we know about derivatives, And then similarly here, well, sometimes the antiderivative will be really easy. If you basically if you integrate 1 dx, you're just going to get back x, and if you integrate 1 dv, you're just going to get back v. So v will be equal to x. So that's pretty good. All right, so we have the pieces that we need. Now let's put it all together. So our integration by parts formula says if we take the antiderivative of this, right, well, we can break it into two pieces. The first piece is the integral, or I'm sorry, the product of u times v. So it's our arctangent times x minus the integral of v, which is x, times du. So we have 1 over 1 plus x squared dx, right? So now we're left with this to integrate. So let me rewrite this step, right? So as usual, I like to put my polynomial first, and then my what we will refer to as a transcendental function. And then this product here is the integral of x over 1 plus x squared, right? And now, let's kind of stop and think for a second. Have we made any progress? Well, in some sense, yes. Because what we've been able to do is to turn this integral, right, that involved arctangent, which we've never done up to this point, and we have no idea what the rule is, right? We've broken it into these two parts, and it still involves the arctangent, which is just a product, so this part is pretty much done, but now we have to do this integral. So it's like we're starting from scratch. It's like, okay, we've made a little bit of progress, but now I have to look at this and think, okay, how do I integrate it? And it turns out what we need to do here now is a u sub, right? So this is such a fun problem. It's like the substitutions just keep on coming. So, we did our integration by parts here. We did our double sub. Say it with me, double sub. So we did our integration by parts, right? Our double substitution. And we made progress, right? But this is not a result that you're just going to see in a table of integrals anywhere. But if I look closely, if I look at the denominator, if I differentiate the denominator, I'll get 2x, and that's close to what we need right here, right? So that tells me now I need a regular sub, right? So let's do this. So for this one, I need a u sub. And what is our u? Well, again, we've seen these types of problems, many of them, where we have u be equal to what's in the denominator. Because now if I differentiate this, I only need one equation for this to work, because when I differentiate this one, I'll get something that's very close to the differential in the problem, right? This, for instance, this is not, we wouldn't have this particular property for the integration by parts. For integration by parts, you need two substitutions for it to work, right? In a regular substitution, again, the ones that are set up to reverse the chain rule, by making this particular u, then we have almost what we need. I can get it to be exactly what we need by multiplying by 1/2. So we have this. All right. So now let's keep writing this down. So then we have our x times the arctangent of x minus, now let's pull out the 1/2, and then we've now reduced it to the integral of 1, and now the denominator becomes my u, and then the x dx, already took out the 1/2, all of those just become my du, right? So now we're almost there. So we have x times arctangent of x, and then when I find the antiderivative of 1 over u, so it's going to be 1/2 times the natural log of u. And I'll even go ahead and put the absolute value in, but then make an observation to show you why it's fine to not have the absolute value, right? Now, because this is an antiderivative, we want our final answer to be in terms of x. So this is where we reverse the substitution. We don't have any limits to worry about because it's not a definite integral. And it looks like this. So we have x, arctangent of x, and then minus 1/2, and then I replace this u with this u. Not the u for the integration by parts, but the u for the u sub, right? So it's the ln of the absolute value of 1 plus x squared plus c. Now, 1 plus x squared for every real number, x, is always positive. So because the inner part here is always positive, the absolute value will not have an effect on it. So in other words, because 1 plus x squared is always positive, so since 1 plus x squared is greater than 0 for all x in the set of real numbers, right? Then the absolute value of 1 plus x squared is the same as 1 plus x squared. Think about it. We know that if you take the absolute value of something positive, it doesn't change. And what we're saying is it's not a specific positive number, it's just that it's always positive for any real number. So then we're justified in writing this as our final answer. So x arctangent of x minus 1/2 times the natural log of the not the absolute value now, just x squared, 1 plus x squared plus c, right? So again, let me write it down, just summarizing what we did. So you look at this. Again, this is not something you would just guess is the antiderivative of arctangent. Just it doesn't look like it would work out, but yes, when you go through, do your product rule, do your chain rule, and a significant bit of algebra, yes, it will happen so that everything just works back out to arctangent of x, right? So a good kind of introduction to integration by parts. There are a few more trickier ones that we have to look at, and I know you can't wait to see. Well, why wait? Just hop on over to the next video and I'll see you then.